Yes, so, do you have any questions about problems, about previous lectures? Oh. Now let's continue. Last time we introduced several functionals like energy functional, integral of u squared, and we used them to prove something. And today I would like to study a bit properties of such functionals. So let me remind the formula. So it was on this object, and the integral over domain D, then R or X, gradient of U R squared, and if, we can actually consider a more general problem. We can consider a functional like this and see how it behaves. So when we studied the Laplace equation, it was sufficient to have just this term. Let me actually add the linear term plus rho of r, u of r. Let's have something like this. So this part was needed when we studied Laplace equation. So it will be relatively easy to see that this part corresponds, this term corresponds to a Helmholtz equation, yes, and that if we turn it on, then our equation will be modified. And this part corresponds to non-trivial right-hand side. So, but to start with, you can think simply about this equation. You can forget about these two terms for a while. So we started this functional, but I also made a statement that the solution of Laplace equation is given by a minimum of this functional. And today I want to explain why it is true and how to study such problems. So to do this, we need some pretty simple ideas and techniques which are called variational calculus. Which is more or less the same as, so it can be schematically called a calculus of functions with infinitely many variables. To explain what it is, I would like to draw a picture. So on the left hand side we have functionals. So let me divide this blackboard like this. On the right hand side, we have a function from Rn to R. So in this case, its argument is a function of x. I can use color chalk. This x is in some, for example, well, let me use a different letter here, R, D, when D is large. So this x is a kind of index. And in this case, we have maybe let me use the same letter for these two objects. In this case, we have an argument with let me write it like this: have u1 and so on, u ud. So we can say that the argument of this function is a function on Rn. So we can write that u is a function on Rn from Rn to R or C. Or it would be R. And in this case, maybe let me write this Rn in different color. And in this case, u is a function from the finite set from 1 to d. So, roughly speaking, to define a function from Rn to R, we need to specify its value in all points, and to define a d-component vector, we need to define the value of all of its components. So in some sense, this index, which belongs to finite set in a case of functions, now belongs to continuous set, to Rn, in the case of functionals. So
I'm not completely clear what you're trying to show here. You put two. Are we comparing these two things, or are they?
yes.
Okay.
So this we can call this. So this is also the index.
That's the argument of the function, and then the function is the argument of the functional.
Yes. So we can think about finite dimensional vectors as functions from finite set to R.
Oh, I see.
I mean,
One is continuous now, so it's more complicated.
Yes, well, in a sense, if you consider functions like this, then this function should be continuous. But if we remove this gradient, then it's enough to have maybe Lebesgue integrable function or something of this kind. So these restrictions become not that strict. So in other words, I can write it in words that a d-dimensional vector is a function from from this finite set to R. And now we simply have continuous index. Maybe let me write it like this. What was one? And actually, we had such examples where functions lived in this finite dimensional space because we started everything from some discrete approximations for APDs. So in that case, this index consisted of several integer numbers, which were both the node of the lattice. So, so it was quite natural from the very beginning. Okay, so are there any questions? So far there were no definitions, actually. So let's go to some kind of differential calculus. So if you want to find the minimum of this function, or at least the extremum of it, then we can naively do the following. Let me first write it here. Let us choose some vector v. So we can write a condition like this. Right? And if you want this to be the minimum, so maybe let me even write global minimum. Oops, right, variable then. So pictorially we can draw it like this. Here we have some function. Mm, we sit in the minimum and choose some direction. Well, this corresponds to u, and then we choose some direction described by the vector v. So this derivative in epsilon is the same as the derivative in the corresponding direction. And it can be written as sum of vi's dy. So this is derivative along with 7 equals to 0. So there is such an object. And if you want to do the same in the infinite dimensional case, then we write literally the same formula. So we choose some function v of x, and say that derivative in epsilon e of u plus epsilon v equals to 0.
Is it going to be an integral
Hmm?
Is it going to be an integral?
Well, by definition. So we simply substituted there and write this condition. Oh, and in the same way, global minimum is defined by the same of those conditions. So Now let us see what happens with this formula. So this is something that we will need to compute, but we can try to guess the form of this expression. Mm. So epsilon equals to 0. Mm. So we see here two objects. We see v of I, this function computed at index I, and we have sum over this index. So since our index in the continuous case is a point of Rn, then this integral, the sum should be replaced by integral. Mm. So we again have v of x, which replaces vi, and mm, this maybe better to say that it goes not from Rn but from D, because we are studying functions on the domain D. So it's a point of D. So, and there is some object which replaces the usual derivative in UI. And this is called a variational derivative. Maybe let me denote x as the index. So, and for this analogy, like this. And this is called variational derivative along v of x. U of x.
Can I ask a physics question?
Hmm?
Why? I'm assuming you're writing this because it's mathematically like true, but why does it become ill-defined in like quantum field theory?
But what becomes ill-defined?
This, well, I guess like an integral over configurations of the field.
No, why do you say that is ill-defined?
Well, I thought it was problematic because you get all sorts of physical divergences, and then you have to deal with them in ways that are strange.
Oh, first it depends on what theory you are considering. If it is quantum mechanics, like one-dimensional theory, there are usually no divergences. But if you go to higher dimensions, it means that it's not a problem of mathematics, it's a physical phenomenon that we cannot define the quantum field theory by simply writing the action. We need to add some extra information. In a sense, there is no field theory defined without any cutoff. So,
So the problem isn't math, it's just physics.
yes. So, uh, mm, oh, the only problem is that naive definition of quantum field theory that uses only the action functional does not work. We should add some extra information. Yeah, but Yeah, what do we have so far? We have some naive requirements that are needed to find the minimum of this function. And we have some formalism. We can also introduce the full derivative. Full differential. How is it called? Also, so actually, well, okay, we have an object uh, like this, and it is in one form actually. Probably you already know them. We have df, which equals to sum of uh, dE, which is sum over d e over du I d ui. Uh, and in this case, it is called not a differential, but variation. And this is denoted like this. Go to the integral over dn x So we can also think about this as about the one form on the infinite dimensional space. Since you can substitute here the function v and obtain this. So we can write that d in d epsilon u of u plus epsilon v is a pairing between v and delta e. So, like here, we can write that d in d epsilon u of u plus epsilon v is epsilon equals to 0. That's a pairing between u and d, dE. And of course, there are also higher differentials. So in this case, they will be called higher variations. For example, delta 2 e will be given by something like d2 e over d u of x du of y delta u of x delta u of y. And here I'm the same d2f. So it's not the external square of a differential, but it's simply a second term in the Taylor series. It will be sorry, it was x, it was u like this. Oh. Maybe replace this derivative with partial derivative because there are many variables. And in our case, we'll have only a second derivative because this functional is quadratic. There are no higher terms. Yeah, and the point is that this variational calculus is not different from usual differential calculus. The only problem is to compute this first or second variation. And let us do it in our particular case. So, what do we need to do? Actually, I probably missed some coefficients that were here originally. We had 1/2, and I would like to add one more 1/2 here. So let's compute the variation of this action, and let us actually compute all possible terms in this expansion. So E of u plus epsilon v in the integral over dn. So I was writing r. So let us say that r and x are the same. So maybe let me change it to x. So we have this quadratic term. So this gives gradient u of x squared plus 2 times 1/2 times gradient of u gradient of v plus epsilon squared over 2 times gradient of v squared. So this was one term. Then and plus the linear term. Of course, we see the original function of u. It is in epsilon independent terms. So let us write this. This equals to e of u, as it should be, plus this integral let us collect all the terms proportional to epsilon. Mm. And plus a quadratic term. So I'm writing 2, it's n. Uh, uh, so on the next step, I would like to solve an equation like this, that for any, where is it? Yeah, that for any function v of x, we should have a vanishing of this integral. But as it is written now, yeah, it is something unclear because we have v and the derivative of v at the same time. We would like to get rid of this term somehow, and we do this integrating by parts. So uh, who can tell what will we get in this computation? So first, which term will we get in this integral? We want to integrate it by parts so that the remaining integral contains only v. Or it can be written like this. So I'll add here this small box. Okay, this should be clear only. Yes. So what will I get if we integrate it by parts?
We can get the minus b Laplace of u
Mm-hmm.
and plus lambda u b plus rho b, and then the first term of the right hand side of the identity, we can use the Goethe's theorem, to do an integral of the bound.
Mm-hmm. Yes. So we get the integral over dd and normal vector times times this vector v gradient of u 7. Mm, yeah, so there is this term plus 7 squared then x Yeah. So, first about this term. Uh, the point is that it should vanish because uh, we are studying configurations with fixed boundary conditions. I actually didn't think about Neumann boundary conditions, but for Dirichlet boundary conditions, I will simply say that u of x, when x is on the boundary, should be some u0 of x, some fixed function. And as we don't want to change this function that is fixed from the very beginning, we should require that variation of u, which is given by function v, vanishes at the boundary. So v of x restricted to the boundary should be 0. And when I write that this exam is achieved if any variation of u is kills this derivative, then any actually means that this v should not change the boundary conditions, so it should vanish the boundary. So this any is any of this kind, any function of this class, from the class of functions that vanish in the boundary. So this term disappears. This term is quadratic in epsilon squared, so it will vanish when we compute derivative and put epsilon to 0. This is just constant. So we are left with just one term that should vanish for any v. So we have some expression multiplied by v, integral over dnx. So this any v. And if it is true for any function v, then we can substitute functions like delta x sequences or functions that vanish everywhere except some small domain, checking in this way all possible points. So it's pretty easy to conclude that if we are restricted to a more or less reasonable family of functions, that they are at least differentiable. we can substitute them into this functional. Then this requirement automatically tells us that this equation should be satisfied. So we see that the Helmholtz equation on the right hand side is equivalent to vanishing of the first variation of this energy functional. And if you ask whether it is a minimum or not, then it's also easy to answer, because suppose that you solve this equation. Then energy of u plus epsilon v is what? Is energy of u plus what is the first non-trivial term that we get in this case? Mm-hmm. Yes. Mm. Gradient v squared plus lambda v squared. Well, this is positive. Get r equal than 0. So it is 0 only if v is 0, or if we put lambda equals to 0, it is 0 when v is constant, but this constant should also be 0 because it vanishes at the boundary. So, in other words, it can be called convexity of the energy functional. Mm. So it's convex, so it has a single minimum that is described by this equation. So let's name this. Are there any questions about this? There is also another nice and maybe simple example in classical mechanics. So if you wish, you can try to compute this variation at home. There is an action functional which is written like this. So it depends on function of t, and it equals to integral from a to b m over 2 dx and dt squared minus v of x of t. And this x.
You say that the second order term is greater or equal to 0. But since for any non-zero b it is strictly positive, then we can say that u is an isolated minimum.
Yes, of course. Yes. There is a single minimum of this functional. So. Maybe the only exception is if we try to study this on a compact surface, so that this boundary term is simply absent. So in that case, we will have we will have a family of solutions on the d-Faraday constant, and there will be a kind of value of this minima. But it is clear from the very beginning that the solution to this equation is unique up to a constant. So, but other cases it's a unique minimum, a unique solution. Yes. So if, in this case, you can compute this variation at home, and yeah, this gives Newton's equations of motion. That m d2x in dt squared equals to minus dv in dx, computed at x of t. Maybe let me better write it as v prime of x of t. So this is remark 1. Remark 2 is that the wave equation has a similar description, but in that case we should replace energy functional with the so-called action functional. So it's also called action. Mm. Mm. There is S of u that is given by again dnx ut squared minus gradient of u squared. And this is called action. It's also let me write this as n plus 1, as if time was an extra variable. Maybe let me even write this time as a separate variable. dt dnx, like this. So in this case, this functional is not positively defined. I think it's not convex, and this should not be confused with the energy functional, because the energy functional is given by this integral over just space coordinates, and it has a different sign here. Mm. the energy that in principle could depend on time, but it does not depend on time if you substitute a solution of this equation. So it was given by this integral. And it actually has the same structure. Uh, so this action function has the same structure as this one. It equals to a difference between kinetic and potential energy. But if you just want to guess on this formula without computing the variation, we can say that all the same computations can be done in the Minkowski metric, which turns gradient squared to such kind of difference between time coordinate and space coordinate squared. So, are there any questions about this? So, now I propose to go to practical applications of this formalism. Because, of course, it is nice to know that all these equations describe minimum of some functions, and actually any fundamental physical theory has a description like this. In the sense, people write the action of this theory and say that its equation of motion, its equations of motion follow from this action principle, like standard model of all elementary particles is described like this. Mm. But technically, this description is nicer than description by PDEs themselves because it has only first derivatives. And if you want to transform something, it is easier to transform first derivatives in second ones. Mm. So, oh, probably should not. No, yeah, it's fine. So, um, uh, let us first consider two-dimensional space and polar coordinates. There are Cartesian coordinates x and y, and there is a radial coordinate r and angle phi. So there are relations between all the any and the new coordinates. Mm. So uh, mm, uh, the question is, what happens with the gradient square if you try to rewrite it in these coordinates? So mm, uh, can you guess this look in this picture? So let us see what happens um, when we change phi or when we change r. So another point on this plane, which we will denote by r. So this will be vector r. And we can introduce two unit vectors. In this direction and probably I can use different for this direction we denote it by er, and in this direction e phi. They are orthogonal and they are unit vectors. In a sense, er squared is e phi squared equals to 1, er e phi equals to 0. Yes, so our vector delta r for small delta. Let us first write it in x and y coordinates. We have here ex and ey in the same way, and ey. So the most naive formula is this: that delta r is ex delta x plus ey delta y. But what should we write if we try to write it in terms of delta r and delta phi? So what happens under the infinitesimal change of r? So delta x and delta y. Imagine. Yes, thank you. So, yeah.
So the vector is ex cosine theta plus ey sine theta.
No, I don't want to substitute all these changes in variables. I'm asking about geometric geometric answer to this question, because of course we could take this change of variable and perform all those changes at the level of Laplacian itself without using all these action functionals. I just want to show a simpler way to get these formulas and to remember them. So, so these vectors are drawn on the blackboard. So in principle, we have everything. Oh, so I want to say that. Hmm?
Are you trying to do the dot product to collapse them?
No, I'm trying to do I'm trying to write this simple expression that it is ER times delta R. That corresponds to simply changing the radius vector without changing phi. It doesn't have a projection on the orthogonal vector. And if we instead keep R fixed and change phi, then we get something orthogonal to ER, something proportional to E phi. But what should the coefficient of proportionality be? So we have E phi times what?
R delta
Mm-hmm. Thanks. Mm. Now, if you want to compute the gradient, uh, uh, what do I want to do? Yeah. So now we know that if we compute the scalar product of this vector with gradient, maybe let me better write this infinitesimal changes everywhere, uh, so that it doesn't miss with Laplace and so on. Uh, so if you compute a scalar product of this variation of the radius vector with a gradient of u, it will be simply du. It will be a change. It will be total derivative of u. So dr scalar product with gradient of u should equal to du. Which means d phi du in d phi like this, in d phi plus d r du in dr. So this is on one side, but on the other side, what should what should we have for components of gradient, so that when we compute the scalar product, we get these two expressions. So this is ER times dr plus E phi times R d phi. So what should we?
What's that symbol
Hmm?
on the right? dr d something partial r.
dr du in dr du in dr. Sorry. So what should we have here to reproduce this formula for total differential? Reminding that these vectors are orthogonal. So there is ER times something plus E phi times something. Where in which term?
And the sine term.
Which?
Oh, I guess
Hmm?
we want to cancel the r on this term with the side, and it's
E what?
phi.
Mm-hmm.
Right. We want to cancel the r, so then
Mm-hmm.
we need 1 over r on the e phi term.
Mm-hmm. Yes. 1 over R, and what else?
And then we need d phi, d phi.
Well, no,
sorry,
device
sorry.
here.
Partial.
Yes, thanks.
Yeah, sorry.
Unify.
And the r term is just partial u, partial I.
Mm-hmm. Thanks. Yes. Yeah. So this expression is equal to the gradient of u written in polar coordinates. So if you now compute the square of this gradient, then it equals to d u and dr squared plus 1 over r du and d phi squared, which is a kind of natural from the dimensional point of view, because r is measured in meters and phi is dimensionless. So we have to derivative squared, and so one derivative is in R, another derivative is in phi, which is a kind of orthogonal to R, but we need to divide by something that has an integral dimension, and so we have this R. And of course, you could do the same computation simply using this change of coordinates and rewriting this expression du in dx squared plus du in dy squared. But it is simply more complicated and harder to remember. So, and one last question, what to do with the integration measure? So, so if we have x and y coordinates, then we can describe everything by squares like this. But for our phi coordinates, we have this squares or rectangles. We have this curly rectangles of size dr times r d phi. So these are the Jacobian of transformation from one coordinate system to another one. So okay, keeping this in mind, yeah, so keeping this in mind, we can write the action as the integral of du in dr squared plus 1 over r du in d phi squared plus lambda u squared r dr d phi. And I'm doing this because now we can compute equations of motion for this functional. So d in the epsilon u of u plus epsilon v at epsilon equals to 0. So who can tell this expression before any simplifications? So just in quadratic form, and we can expand it like this, keeping only cross terms, which are linear in epsilon. Oh.
So that's the hold on, it's great.
Hmm? What is the problem to compute this? Is the definition unclear or? Uh,
This is already the gradient of the function squared.
hmm?
This is already the gradient of the function squared.
Yes, of course.
Yes. Then
It's,
we just to push it in the direction of the vector v a little bit.
yeah, since you simply substitute u plus v here and expand up to the first order in epsilon. Mm. Hmm?
It's v times minus second derivative.
Wait. Have you tried to integrate it by parts immediately or not? But let us maybe write the preliminary, this expression of the preliminary.
Only the past with epsilon.
Yes.
Okay, so it's epsilon times.
Oh, I'm differentiating and put an epsilon to 0, so we need just that part. Yes.
They use the derivative of u on n times the derivative of v on s
Yes.
plus 1 over n squared, the derivative of u over v, the derivative of v over p,
And
plus lambda
UV. Yes. Thanks. Yes, and now we need to integrate this by parts. as you correctly mentioned. So if we integrate this by parts, then we should remember that there is r here, which does not commute with the r derivative. So the result of integration by parts is the following. We have minus 1 over r d in dr, which acts on r du in dr. So one expression in this integral by parts was r times du in dr. Another expression was dv in dr. And so we moved this derivative from v. And let me write it like this. We moved this derivative from v to the rest of expression, which was r times du in dr. We don't have such a problem in the second term because there is no phi in the integration measure. So this term will be minus 1 over r and times b. 1 over r squared d to u in d phi squared times b plus lambda uv times r dr d phi.
I don't see how you got the second expression because all those integrals have epsilon on them. This over here on that board.
But what?
Not the integration of parts, but the first step.
But we expanded up to first order in epsilon and then differentiate in epsilon and put epsilon to 0. This procedure keeps on with
the differential, the derivative of the epsilon.
Yes. Yes. So if we say that it is 0 for all v, then we get an equation. And this equation is the following. So v appears as an overall factor everywhere. So the equation is lambda times u equals to what? To this expression. 1 over r d in dr r du in dr plus another term. 1 over r squared d u in d to u in d phi squared. So, but what was our original equation? So if this u was written in Cartesian coordinates, then this expression would be lambda u equals to Laplacian of u. Or if you write it explicitly, it was d2u in dx squared plus d2u in dy squared. So all these expressions are equivalent. So we conclude that a Laplace operator in the polar coordinates is the following one. Sorry. or we can compute this derivative. So what will we get if we differentiate this term?
Partial U plus partial R partial squared.
Yeah, so
R squared.
yeah, so there is this main term, and there is a first order correction plus 1 over r du in dr plus 1 over r squared d to u in d phi squared. So this is a Laplace operator in polar coordinates. And it has the following form, which also holds in higher dimensions. So we'll see it for the three-dimensional space, but in principle it's always the same. So oh, it looks like this. It is dr squared plus n minus 1 over maybe let me write as Laplacian r plus so it's in the general case plus 1 over r squared Laplacian on s n minus 1 and we need to write who they are. So radial part Laplacian is dr squared plus n minus 1 over r dr. So this corresponds to n equals to 2, and the origin of this coefficient is that the integration measure for the n-dimensional space contains r n minus 1 here, because this is how the volume of Sn minus 1 behaves. And this second Laplacian should be written in some nice coordinate on a sphere, and we'll write it explicitly only for n equals to 2, and we already have this expression. This 1. Which can also be denoted by Laplacian phi. This equals to d phi squared. And we also have an explicit expression on S2. We will write it probably the next time, or maybe the next week. Yes, and of course, if this looks too complicated, you can simply take this change of coordinates from xy to r and phi and transform this expression to new coordinates. And then this simple form would appear as a miracle. But if you know arguments like that, then this expression should look absolutely natural to you. So, are there any questions about this? In principle, if something looks too complicated, you can simply do this computation at home to transform this combination of partial derivatives using this change of coordinates to r and phi, and see this expression. Yeah. Now let us try to use these formulas somehow. So in the Cartesian case, we could perform separation of variables, saying that we can diagonalize simultaneously two second derivatives in x and in y. But here we are in the similar situation because we have some operator that depends only on r and some operator that depends only on phi. So we can try to look for functions that diagonalize both of them. Or maybe we can start from some specific equation, for example, from the Laplace equation, because it's the simplest one. So we have a second derivative in phi, and we know that phi is periodic. So we can say that u of r and phi can be written as a Taylor series. As a Fourier series in phi. So we can perform this kind of partial Fourier transform. So d and d phi squared acting on I and phi gives minus n squared e to I and phi. So what happens when the equation on un if you substitute it into the Laplace equation? So we will have this for a series. And what will we have inside? So the operator is written here in whatever form you like.
So you're only transforming the phi variable, right?
Yes.
So then you have the second derivative with respect to r,
Mm-hmm.
and then you also have 1 over r times the first derivative with respect to r.
Yes.
And then you have minus
Thanks. Yes, thanks. And um, what if we try to solve, if we try to solve a Laplace equation, in a sense, we ask this to be zero. So we have this infinite set of equations for each mode, and I don't know how to solve them. So we have 1 over r squared, so we can multiply everything by r and get an expression like this: r squared dr squared plus r dr times un of r equals to n squared. And do you know what to do in this expression?
Also, the solution is a product of r times a function of r times a product of phi. If there's symmetry.
Wait. Where? What function of phi? We have a single function of r. Yeah. I just performed the Fourier transform to the very beginning. The question is how to solve this kind of ODE. Uh, yes, there is such kind of name. But,
Is equal to e to the t.
yes. So no, it's just an ODE. And to see this change, well, we can of course perform this change of variables to exponential variable, but we can first notice that this operator can be written as a square of RDR, because so let's do this computation in the corner, that RDR squared is RDR, RDR. And since this derivative commutes with r by 1, it is r squared dr squared plus the commutator, which is 1 plus r dr. You can imagine that you are differentiating some function like this. Let's substitute here some function. And this means that we can either differentiate drf, or the derivative, or we can differentiate this r, and we are left with a single r derivative. So this is r d in dr. Squared u equals to n squared u. And now we can rewrite this r d in dr derivative as a derivative in log of r. This is precisely this change of variables to exponential variable d in d log of r squared u equals to n squared u. So, and what is the solution of this equation? This is un. Yes, but what will it equal? No, y n squared. Yes. Well, and with plus minus sign because we had n squared, right? So n is defined up to the overall sign, right? Uh, so what does this equal to?
It's like r to the n or r to the minus.
Yes. Thanks. Hmm. Yeah. Uh, so we have found this uh, uh, polar modes for Laplace equation. So expressions like r to plus minus n e to n phi uh, uh, are killed by Laplacian. Oh, and we can use this knowledge about this power modes to solve at least one boundary value problem with the Laplace equation. So far we are studying only square domains, but now we can consider a disk. So of radius 1, for example. We can solve the following boundary problem that u at Laplacian of u of r phi equals to 0 for r less or equal than 1, and u of 1 phi equals to a function u0 of phi. So suppose that this function has a Fourier series, and some of this function is relatively nice. So we can write it as u0 n e to n phi. So then, can you solve this equation? Can you write an explicit formula for its solution? we already have an infinite number functions of this kind that solve Laplace equation. So can we construct some combination of them such that it has this boundary condition and is well defined for r less than 1?
We have to use the constraints. It's like, I think, the sum of the integers
Mhm.
of because I think I needs to deduct product with the exponential, so I think we obtain u 0n r to the n
Mhm.
e I n.
Yeah, thank you. So it was as simple as a solution to this kind of boundary problem, maybe even simpler, because we did not need to adjust any essential cost functions. We could simply use this simple modes. Yes. So, do you have any questions? So next time we will continue studying this. We will study this question other domains, and after some time we will switch to 3 dimensions and study some special functions, like Bessel functions or spherical harmonics.
So what is the main tool for solving boundary value problems?
Either to well in all cases when they can be solved no, maybe it's oversimplification. No, there are various tools, especially in the two-dimensional case. The main tool would be conformal maps. So this maps using normal modes work in some situations, but the most generic one is using conformal maps.
For 2 dimensions.
Yes.
When we talk about 3 dimensions?
I think the only way is to choose some nice coordinates, and if you are unable to do this, then you can only solve it perturbatively. So the mm, ellipsoid coordinates, maybe the more generic ones, and maybe that's all for 3 dimensions.
Bye.
Bye. And also there are some naive examples like mm, domains bounded uh, by planes. In that case, you can use some reflection methods. And if if those planes are located nice, then sometimes you can even compute the sum explicitly. So.